Hello, everyone. Welcome back to advanced track number 5. Today, we're going to be talking about PyTorch and backpropagation. Basically, we're going to be giving you a quick little introduction into what PyTorch is and how you can kind of build more modules with it to prepare you for the guided project next week. And we're going to be talking about backpropagation, which is one of the most important parts of any machine learning package. In fact, most machine learning packages can really be boiled down to a little backpropagation machine with a bunch of really quality of life improvements put around it. Basically, if you don't know what that is, backpropagation answers the questions or gives us a solution to how in the world do we compute gradients? How do we take the partial derivative of the loss function with respect to all our weights so that we can do things like gradient descent and our network can actually learn? So that's basically what we're going to be covering today. This will be a little bit shorter than usual, but backpropagation is kind of the most math-heavy thing that we're going to be covering, so it will not be the most straightforward thing, but I hope that our explanation will be good enough for you to understand. So again, the mandatory links, the asset cluster is here, which should contain the slides for today and also the recording last week for those of you who weren't here, and then link to our Discord as well. Let's begin.
So today we're going to go over just like the very basics of PyTorch. We're going to tell you guys everything you need to know in order to essentially code up the guided project that we're going to be doing next week. So if you guys do want to follow along with all of like the different modules we're going to be going over, here is the tiny URL to the collab notebook. And yeah, it just allows you to interact with the code that we might be showing on the slide today. But yeah, this is just for your own like information. You can like choose to like play around with it or not.
You think it's the best way to install Python? Because you install through Conda or on Mac, Conda, Beautiful Soup, or just through homepage?
If you want to install locally, definitely Anaconda. Like I would say Anaconda is probably the easiest one if you want to deal with like again, like we talked about it last time, but like managing your virtual environments, it will definitely be Anaconda. And like if you are comfortable with the command line interface, I personally prefer it a little bit more, but then the graphical user interface also works quite well. So if you just look up like Anaconda,
yeah, I know all the ways, but I was just curious because
that's what I use about it. Anaconda, for those of you who
recently reinstalled through homepage, and I just found out that it's the worst way to do it.
Oh yeah. That was installed via like pip directly. We just have the links here in case you guys are, but like if you want to install it directly, it's usually pretty painful because you have a lot of version conflicts got to deal with, especially if you install in like your base system installation of PyTorch. Because for those of you who use Macs, it comes with an installation of Python, but we typically don't want to mess with our base installation of Python, because if we mess anything up with like environment variables or anything like that, to reinstall it will be kind of tricky because it is the base installation and some other apps may be reliant on it. So that is why we suggest to use things like virtual environments with Anaconda. But today we're just going to be using basically a cloud version of this that does everything there for you, which is Google Colab.
Link. Yeah, another great thing about PyTorch is that it has really great documentation. So here's just a link to like the PyTorch doc. So like if you ever have like a function you're not so sure like how to use them, they have very, very detailed information about like how you're able to like use all these things. So definitely would recommend. It'll help a lot in the future as well as for the guided do next week.
It's a really fun thing. If you are the type of person to do this, but like PyTorch on their documentation links directly to the source code, and their source code is very, very readable. So if at a certain point you want to figure out what's really going on behind the hood, it's actually pretty informative just kind of going through your website and digging around.
So for the documentation, definitely go check it out when you have the chance. All right, yeah, so the first topic that we're going to talk about today are tensors. This is essentially kind of like the way that we're going to be able to like represent most of our data. So very, very important. Yeah, so think about torch tensors as just kind of like an array. Like, are you guys all familiar with like what arrays are, like lists and stuff? Yeah, okay, solid. Yeah, so Yeah, just kind of like another word for array, but it has a lot more properties which are very helpful for AI. And yeah, this is just what we're going to use in order to like store our data, like our outputs, our labels, as well as like. And so this is the way that we are able to initialize a tensor. Yeah, so if you guys have like your notebooks open, we should have this line of code for you guys to just like play around with. So you essentially call the torch library, which is this one right here, which should be imported on the notebook already for you guys. And then in order to just create a tensor, just .tensor, and then you can put like whatever you would like. Typically, we just use like simple like Python lists. Yeah, and then when you like print out Y, you get a tensor with all of the values that you can put. So pretty neat stuff. And here's just other kind of like fancy tricks that you can do with like tensor initialization. So you can do like torch.ones, which will just initialize like all of your tensors to have values of ones, and then torch.0 will also give you all of your tensors with a bunch of zeros. And when you call these functions, you can specify the dimensions that you want to work with. So as you can see here, we're looking at 5 separate like lists of like 2 by 3 dimensions. So do these function calls as well as parameters make sense to you guys? You guys have any questions? Okay, perfect. Yeah, and then torch.rand, I guess you can infer that it is just like a bunch of like random like numbers here. Yeah, so yeah, this is just kind of how we initialize tensors and just stuff. And so one really great thing about tensors is that we're able to manipulate the dimensions very easily, which is really great because like when we're going from like layer to layer through like our feed forward or like backpropagation, we always need to make sure that we have a way of being able to control like the shape of our tensors as well as our data. So one really great thing that we're able to use is torch.reshape, which is, as you can see right over here. So in this line of code, we have a equals torch.tensor, which we have like 2 lists of like 5, 3, the others like 2, 7. And then when you print the size out, which is like right over here, we get that this is 2 by 2, right? And then however, when we do torch.reshape, we pass an A as well as the new size that we want it to be, which is 1 by 4. We can see that when we print out B, we actually get our new tensor, which has the exact same values as A, but just in a different format, which is right over here.
Yeah, and another thing of like why do we want to do this is because, for example, if you're doing something like like a normal math operation, like wx plus b, right, and you're just kind of trying to pass your input here through some sort of matrix multiplication, you can think of your input as some sort of like oops. You can think of your input as some sort of like vector of values like this, because we're kind of stretching an image into a vector and then passing it through fully connected layers. For CNN, it's a little bit different, but like something like that. Because we're doing that, sometimes this thing, X may have a dimension. Whatever. X may have a dimension of if you're thinking of this vector as a matrix, it will have a dimension of n times 1, n being the number of dimensions it has. However, when we're storing this X, we may not have it as n times 1. We may just have it be n, right? It's just a list of vectors. And we're actually doing multiplication. PyTorch will get angry at you, being like, that's not a matrix. That's just a one-dimensional vector. So in these cases, that's when you have to do things like torch.reshape to shape it, to kind of add that auxiliary dimension there, so you can do things like vector multiplication. Or if you want to go the other way around, use torch.squeeze to get rid of dimensions that's just these auxiliary dimensions. And there's also a kind of opposite function to torch.squeeze, which is torch.unsqueeze, which basically you can add these auxiliary dimensions that you can use to help like basically be able to do things like matrix multiplications with the correct shapes.
So yeah, exactly. Jordan just said about squeeze. Yeah, so as you guys can see over here, that when we run this tensor that we've had already like reshaped, size becomes 1 to 4, 1 by 4, right? However, when we run it through torch.squeeze, you can notice that it gets rid of the 1, which is right over here, and we're just left with 4. So yeah, these 2 functions, very necessary. Make sure you familiarize yourself with them, and yeah, you're gonna need them quite a bit when you start coding up like projects and stuff. And then some other like helpful operations with tensors is that we're able to add tensors together, which results in like element-wise addition, as you guys can see over here. If we have two tensors x and y, the elements that correspond in the same spot will end up getting added together. So just like matrix, like adding like two matrices. And then when we multiply tensors, it results in wise multiplication. And, yeah, just to know, it is not dot product multiplication, but it is actually. Does this generally make sense? No question. Right. And then another really neat thing that we have at our disposal is torch.matmul, which stands for like matrix multiplication, which we have over here. So yeah, if we have two matrices and then we call on the function, it'll just essentially do everything for us. You don't have to do it by hand, which is like pretty neat. Are you guys all familiar with like some stuff?
Is it which one is the tensor torch row or a column? If we think of it as a normal matrix.
So this would be like one row, okay. And then when you stack them together, they'll be like your columns.
So imagine like 2, 7, 3, 4, 3, 1, 5 that way.
Yeah, so it'll be like 2, yeah, 7.
Just regular. Okay.
Yeah, and then so like yeah, so your rows will all be in like one bucket together, and then your columns will just be like if you take so like one like pair of brackets, like another pair of brackets will be your next row, and then your third row will be your final pair of brackets. Does that kind of make sense? Yeah. So like with this one, our first row would be this array right here. And then our second row would be this array right here. And then so our column count would be 2. Does this make sense to everybody?
Never mind. Okay, let me get back to my bad. I am stupid again. Are you still sharing your screen? Okay. Let's see. What the heck? Oh. Oh, switch. There we go. My bad. Okay.
So now that we've like familiarized ourselves with like tensors and how we're able to like represent our data, we're going to get into the first part of just essentially any project, which is being able to configure your data. So like loading the data itself, which is pretty important because if you don't have data, you can't really. So what is really nice is that Torch gives us they just give us like a lot of like functions that we're able to use in order to essentially like work with our data. And so as you can see over here, we're able to make our own custom data sets, as you can see over here with like classes. And then another really great thing that we have is that we have access to the get item function as well as like the length function, which is like over here. Right, and then yeah, so one really nice thing is that we're able to build our own data sets, and they also have data sets that are available for us to use as well. And so if we want to see this in action, essentially is that like we can see through this line of code, we have our inputs, which are like these two sentences, right? And then we have our labels be true and false. And then essentially all we have to do is just call upon the custom data set function that they've already defined for us and input what our inputs are as well as our labels, right? And then this will become our new data set, which is our fruit data set. So this is kind of like a nice thing you can do if you just want to like be able to like create your own data sets to like train on. And then if you notice that when we like print like fruit data set dot get item, like the first item, we get the very first item that we had inputted. And then when we want to find the length of our data set, we get 2.
And just another quick thing. Is everyone here familiar with class inheritance? Of like, yeah, okay. So, okay, just making sure, because the reason why we're kind of defining these seemingly arbitrary functions here, but like not actually writing out, let's like, well, how do we actually get an item is because this torch.utils.data set has a lot of built-in methods that will request things like get item and length and length for you to be able to load data. So basically what we're doing essentially here is basically overriding these functions to be like, this is how I want to actually load my data sets. And like, for example, the length function is like a very specific sort of Python thing where like if you remember how to get the length of a list, you do len open bracket to list close brackets. Basically what that's actually doing is it will be going to whatever thing you have inside, because remember everything Python's an object, and it'll basically look for this len construction and say, what does that return? And that will get you the length of the list. And that's the same thing here with data sets and how you would get lengths of data sets.
Yeah, this is how we're able to make our custom data sets using Torch, which is like pretty helpful because whenever you need to like import something, you're able to just use this and it'll like configure everything for you.
Generally, with the things we're doing, we don't really need to do this because PyTorch has like built-in data sets like MNIST or CypherR10 that we'll see next time that kind of has all of these written for you. But whenever you're doing any sort of machine learning research where we have even like remotely custom data that's not in the default sort of built-in thing, you'll like all you will be given is, let's say, like a folder of JPEGs or like, a folder of JPEGs with the text file that corresponds to each JPEG, file name to what class they're in. And then you'll have to like kind of dig into this custom data set object to then say, okay, how do I load these things? And you will have to do a little bit of finagling with like, loading images and parsing text files and stuff like that. But like the idea still stands that, you have that flexibility to be able to load whatever you want, as long as you're using these kind of class constructions that PyTorch can then use to, wrap in this nice, neat data set object.
Yeah, so you don't really need to understand how to use this too much. You're not going to really use it that much, like I guess like in projects or like the guided project that we're going to do either, but it's just something nice to know. And so another thing that we're able to do with our data that we've loaded onto Python or using PyTorch is that we're able to now kind of like play around with the data set. We're able to like manipulate it as well as like shuffle it and just do whatever we might need to do in order to get the data like ready for training. And so some things that are very typical that we like to use are like the delete load on the data set, which essentially just like loads the data. And then when you reorganize the data set into batches, as you can see over here, you can determine like how many batch sizes you want. And then you can also shuffle the data if you feel like that is necessary. So as you can see here, you just have like many options with PyTorch on how you can like configure your data before you start your training process. So as you can see over here, we're able to like load our data as well as we're able to like break it up into batch sizes, and then we're able to like shuffle them. Does this kind of make sense for you guys? Yeah, so what this is just essentially showing is that we're able to take our data set, which is our fruit data set, the same data set, right? And then we're able to break it up into two different batch sizes as well as like shuffle them. So here's the first one when we break it up into like different batch or one batch size, and here's one when we have batch size 2. Yeah, and then again, one really great thing about PyTorch is that we do have a lot of built-in data sets that we're able to use just like right off the bat. And so for this workshop, we're going to be actually using the MNIST data set, which is the handwritten digits. And then typically, I feel like people also like to use like CypherR10 as well. But yeah, in order to just get it, you can literally just like do like torch.vision or torchvision.datasets like .mnist to like get the data that you want. And you're able to or how you essentially want to like and then one really nice thing that you can do is that you can break up the data set into your training data set as well as your testing data set.
And in case you're wondering, PyTorch has a lot of data, like all of this, they're all different variants of just like, data. And this is just a package that's kind of a subsidiary of PyTorch called Torch Vision, which has a lot of these stuff. So like, yeah, you're probably going to be fine with all these kind of preloaded stuff.
Yeah, and then so what this is essentially doing is that it is telling your program to go get the data, right? And then over here is where you're going to be able to load the data to be able to use throughout your program using the data loader. So does this kind of like make sense to everybody? Does anybody have any questions like regarding like why we do this or? Yeah, and then another great thing that you can use, this is like optional, but like definitely very, very helpful, is that you can visualize your data using matplotlib, which is like matplotlib library. And then yeah, so essentially it just allows us to be able to like see what we're working with. Like if we don't use this library, like we literally wouldn't have like these graphs that like show like the pictures that we're working with. Yeah, it's not necessary, but like definitely very, very helpful if you're trying to like troubleshoot, or if you just want like verification that like, okay, like I've learned everything, like everything looks about right. Yeah. So this is kind of like the code that you use to essentially just like visualize your data, and you can see over here. And then the part that you just have to really pay attention to is this line right here, where we essentially use the math library.
One very important thing that I want to clarify with PyTorch. PyTorch, unlike basically every single other machine learning package that's ever existed, instead of because if you remember, with an image, you have your height and your width and your number of channels, right? So your image will be in the shape of height, width, channel, right? So this is with most other things, and also how Matplotlib also expects your image format to be in. However, with PyTorch, they do instead channel, height, and width. And if we just feed the usual sort of PyTorch image into Matplotlib and you do plt.im show image, it's going to freak out and say, no, this is not a valid format. So what you instead have to do is do image dot move axis, and we want to move the 0th axis to the third to the last place. We want to do 0 and then 2, right? We're moving the channel axis from the 0th axis to the 2nd axis. So that's if you see like in our future demo code of like this dot move axis thing, that's why we're doing this, because PyTorch does channel height width, so with height width channel, which most things expect.
So that is basically just a nice tool at your guys' disposal for like visualizing your data, as well as like anything that you can do with it. So now that we have figured out how to like load our data, how to configure our data, the next step is to get into like the actual like machine learning model itself. So essentially, when we start with building a model, we define our model through like the already defined class that Torch has, and essentially we just like inherit everything from it. And then so essentially what we can do is that we have our custom model, which is right over here. And then in the init function, or like your constructor, you're able to define like your submodules. Typically, you're going to have like all of the layers that you want over here. And then you'll also have a forward function. And so as you guys can probably imply from the name, this is going to be the way that we forward propagate in our, or like feed forward in our like machine learning model. And yeah, so like whenever we have like this class, this is going to be the function that's going to be called in order to get everything started. Yeah, so exactly. So essentially your function will automatically invoke the forward function, which is right over here. And as you can see over here, just essentially everything that I said in the previous slide, in our constructor, we just have to define our layers that we use with like the dimensions. And then in our forward function, we then call upon these layers in order to start the feed forward process. Does this part make sense to everybody? Any questions?
And just to kind of clarify, you will also kind of see this a lot in a lot of PyTorch code, is this capital F. And you'll be like, what does that even mean? So this is kind of just like what people generally do with PyTorch. Is PyTorch has this kind of submodule called torch.nn.functional. And basically what it does is it provides a functional interface to a lot of operations such as ReLU. And if you're wondering what that means, if you take a look at here, right? When you do self.layer1 and then .linear, what that linear is actually a class, right? What we're doing here is we're initializing a class which is a linear layer, a fully connected layer. Then we can then call that class, because that class has a call definition, a forward definition being defined there. It is also in that module. Like PyTorch networks are actually just a bunch of inbuilt modules nested within each other. But with ReLU, we won't just call it directly because ReLU has no trainable parameters, right? It is just kind of one thing that always does the exact same thing when we pass it through. It chops off the negative values and makes it 0. So we can define a layer that contains ReLU. Like there's nn.ReLU, I believe, is a function. But because it always does the same thing, we can just use the functional sort of interface for it. Does that make sense? The difference between like the initializing a class as a layer in PyTorch versus just using a function. That makes sense? Okay.
So meaning like f is nothing, basically.
Oh, f is actually usually what we do is we will do import torch and then functional
Oh, I see.
as f. Yeah. So it's really just an alias for this whole thing. Yeah. Okay.
And so that is pretty much how we just like initialize our model, essentially. And then just for like a before we move on to the next section of like training, just like a very brief review of like what gradient descent is. Yeah, so as you remember with gradient descent, we need to be able to like optimize our model, right? Like we need to be able to actually like learn and figure out like, oh, like if this is not right, how do we adjust to make it more correct at least, right? And so that's where gradient descent comes in. And essentially we have to be able to calculate or which is like how much we need to be able to update each of our weights according to like how well it did, right? And the process of calculating G is called backpropagation, which we're going to go over in the other part of today's workshop. Yeah, so this is just remember that gradient descent is needed in order to just help our model optimize as well as learn. And then yeah, just one thing to note with gradient descent is that it can be susceptible to like little flaws. With that just essentially means you want to find the one. However, sometimes there might be like a couple other dips. And so yeah, like when training, you have to be careful because you don't want to train too like hard or else you might accidentally end up like in the local minimum versus like the global minimum. And so in order to avoid that issue, this is where we have this thing called mini batch gradient descent, right? And which this essentially is just kind of like how we're able to calculate gradients throughout like the training process. And essentially it kind of answers like how many gradients do we need to calculate at once, right? Because if you think about it, if we try to calculate all the gradients for our data, you might not have enough power to do that. But if you go to the other extreme and just do it for like one input, then your gradient descent becomes very unstable. So the solution is to fall somewhere in the middle of like 1 and all of your data, which is like sum inputs, right? And so what this means is that you just essentially calculate or just run gradient descent on like small batches of your data at a time. So you'll still run through the entire thing, but you just don't feed it all at once. Does that kind of make sense to everybody? Yeah, and so essentially this is kind of how it is visualized. So basically what we're going to do is that we're going to have like our entire data set, right? We're going to break it up into small batches. So let's say like 5 groups, right? And then we're going to run the feed forward inputs on each sample within the batch. So on the first group, we're going to calculate the weight and biases and partials in the loss function, right? And then we're going to be able to like take the averages and just like update our weight and biases according to like how we did. And so after that batch is done, we're going to go to the second batch and do the exact same thing. Yeah, so what this ensures is that we're able to train in a very like efficient but also stable manner. Yeah, and then the word epoch essentially means just how many, like just like one rendition of your entire data set. So if we broke it down into 5 batches, then it's like one rendition of all 5 batches. And then if I did 2 epochs, then I would just essentially have run my entire data set twice. Does this kind of make sense, like what batch and epoch means? Okay, so now that we've kind of like set those definitions, we're going to get into actually training our model with our data that we've like already loaded. And so, yeah, essentially for training, we really only need 4 things: our data, which we've already covered, as well as our custom model with our word function and class, and then we also need our loss function as well as an optimizer. Yeah, and so, yeah, so these are just like the 4 things that we're going to be looking at for training. And so essentially what this is showing is just kind of like the visualization of like how we train. And so as if you look at this like code here, what this is showing is that this is us running through our data set essentially 10 times, right? We're doing 10 epochs, so we're going to run through the entire thing 10 times. And then for every data within the training data loader, right, we're going to break it up into our inputs as well as our labels, and we're going to get that from our data, which is right here. Then we're going to reshape our inputs to the appropriate dimensions. And then we're going to essentially, yeah, so after like, so when we do this, the feed forward network has already been called. And then afterwards, actually, no, my bad. So we set the optimizer here. And then in predictions, we run our feed forward function. And then after we do that, we have all of our like predictions, right? And now we have to evaluate how well our predictions actually work, our loss function. And then after we have calculated our loss, essentially just like how good or bad our model is doing, we're going to backpropagate. And then we're going to be able to optimize from there. And so what essentially this is kind of showing you is that we just do this process just many, many times for every single like input. And then we do it for like many epochs. Does this kind of make sense?
I have a question about the clear the gradient buffer thing. So I previously went through the PyTorch documentation saying that if you didn't call that zero grad thing, it will kind of stack the gradient together. I'm just kind of confused. What is that exactly?
We will actually talk about it during the backpropagation part. We'll be kind of demystifying what exactly this is doing. So on your horses, we're going to be talking about it very soon. Yes.
So when we just do dot backward, it just knows how many layers and neurons we have.
Yes, and basically this is backpropagation. This is where it computes the gradients, and it knows how our input has gone from from input all the way to output because we're building something called a computation graph. And again, we're going to be covering this just in a very short bit.
I was just curious because I did backpropagation manually, and it's a lot of, we have to know a lot of things in between.
Yes.
To do backprop, and I was just curious, how is it doing just by doing?
It is basically keeping like a kind of cache behind the scenes of like where everything is. It's building a computation graph again, kind of just behind the scenes, and those are typically stored within the tensor itself. Like the PyTorch tensor object is actually a very, very complex object. Like you think, oh, it's just like a list. No, it's like a list with a lot of different properties and a lot of entire computation graphs that can be stored within this tensor itself. So it's kind of, you can think of it almost as a linked list, where like each tensor basically tells you where it was in
that makes sense.
right before, and it keeps a cache of like
kind of.
Yes.
Is it like a linked list?
It's kind of like a linked list. Like if you take like ACM 147, which is the deep learning class, and you were to do this by hand, the way you would do it is kind of also sort of like a linked list, kind of. But like basically you have to keep like a cache of all the objects that you will need to do backpropagation later. And again, we're going to be talking about this, in just a little bit.
So this is essentially just kind of like giving you guys like just like an overview of like how we train, just like the steps. And then we're going to get into like more detail on like these last two right over here. And so essentially so this is going to be our training, right? And so this is where we're like training our data, kind of like optimizing, like updating our like biases, right? However, final one, when we want to actually test our model, right, we're going to do something that is very similar to our training. However, with our testing, there is no epochs, it's just one big thing, right? And essentially with our testing, we are no longer trying to like backward propagate or like optimize, because this is just kind of like our test. This is like our one run through. And essentially this is kind of like what we show over here. So it's very, very similar, as you can see, but instead we call the test data loader instead of the training one, right? And then we essentially just run it through the forward propagation, which is right over here. And then from there, we just tally up how much we got right and wrong, and then we get our accuracy count. So very, very similar to training, except we just don't do like this entire last part over here, because testing we only run through it once. this makes sense, like training versus testing and why they're slightly different.
And again, the minutia of a lot of these syntax stuff, we'll get into it a little bit later as well.
Just remember that for every like project that you do, you will need to train and you will also need to test.
Yeah.
So that is essentially why we break it down.
And here we didn't bother to split the trained data set into train and validation. That is good practice, but again, for demonstration here, we're just going to use the test data set to test it. But remember that if you in the real world, if you use the test data to change your model, you actually be overfitting to the test data set, which is not something you want to do.
Yeah, and so the test data set is ideally data that your model has never seen.
Yeah. Not only your model has never seen before, you have never seen before.
And that's true.
Yeah. So like one of the ways, for example, a lot of like machine learning competitions that will do this test data stuff is they will give you the test data itself to let you basically debug and make sure your model can actually pass through the test data. However, they won't give you the corresponding labels for the test data, so you don't know what your accuracy is. And what you will do is you will pass your test data through, create basically this list of labels, which are your predictions, and you submit that list of labels as your predictions. And you use that list of labels of predictions to then basically calculate what your final test accuracy is, because they want to make sure 100% that you've never seen the test data set and that you've never seen how your model will do on the test data set. So it's truly a sort of evaluation of how well your model can generalize.
That is training and testing. Yeah, and then visualizations, yeah, just so like kind of like a sanity check sort of thing. We can once again use like matplotlib in order to just visualize like our model's performance essentially. Yeah, so you can kind of see over here, like using matplotlib that we had like showed earlier, we can just see like, okay, yeah, like the prediction is 4, the label's 4, and then like we can visualize like, okay, it's actually 4. Yeah, this part's not necessary. The other two you have to have, but this is just kind of like a nice tool to have like in the back of like your toolbox. Right, and then one other thing to just talk about is just like saving your progress, right? Because like you're not going to do everything in just like one sitting, right? You might want to like save like your training weights and stuff, and then come back another day and just like reload and start right where you started. Essentially, you don't want to have to like start from scratch every single time, because that is not efficient and it will just waste a lot of time and energy. So essentially, what you can do is that you can save your model using torch.save, right? And then it'll essentially save everything that you've kind of like done so far in its like own dictionary, right? And then in order to just like load the model that you saved, you can just call it again right over here using like the patient that you saved it, and then it'll essentially just kind of like load everything back on, and then you can get like started right where you had left off. So these are just kind of like nice things to just know in order to just like not have to deal with like a bunch of like having to restart and stuff.
Yeah. Oh, and kind of one additional thing about this. So right here, what we're doing is we're saving the current state of the model, the current weights of the model, as we're kind of halfway through training or something like that, right? But if your plan of saving and loading a model, like when you load a model, you're still planning to train it even further. Sometimes you may also want to save the state dict, or basically the state dictionary of basically it describes the current state of the model, but you also want to save the state of the optimizer as well. And the reason is because sometimes, like if you think about like more advanced optimizers like stochastic gradient descent with momentum or atom, it's keeping like usually a sort of moving window of gradients or magnitudes of gradient or something like that. If we don't save that, what happens is even though your model is kind of just trained halfway, because you haven't saved the state of your optimizer, it doesn't remember what your kind of like moving window of gradients was. So you're almost like starting from scratch with building this moving window of gradients. So the behavior of saving a model halfway and then starting to train it again will be different than if you were just training the whole way. So sometimes if you're using more advanced optimizers, basically anything besides just normal stochastic gradient descent, you will probably want to also save the state of the optimizer itself too. But then again, like you're probably not going to deal with this unless you're training models that take so long that you have to pause it because you can't just let your computer explode or something.
So for this project that we're going to be doing, as well as like the projects in like the project track, you won't really need to deal with this, but it's just kind of like, once again, a nice thing to know and be aware of. Yeah. All right, yeah, so that was just kind of like the rundown of like basic PyTorch functions that we are going to be playing around with a lot more next week when we do our guided project. Yeah, so now we're just going to take like a quick like brain break so you guys can just kind of like process everything, and then we're going to jump right into back.
Okay, are you guys ready for math? Okay, cool. Let's begin. So basically, right now what we're going to be talking about is something called backpropagation, which is the process of basically saying how do we compute gradients. And I'm going to be talking about this from kind of like a more PyTorch focused perspective, which is how does PyTorch do this? How does it know that you have kind of passed your vectors through things, and how does it use that as information to be able to do backpropagation, to be able to compute the gradients? So to do so, we want to first, let's see. All right. So remember the training code that we just showed right there? One of the questions that came up was, what in the world is dot backward? Backward, how is this gradient descent? And what does optimizer the step that follows it do, right? So to do that, we have to answer the question, how do we actually compute the gradients? And the answer is we use matrix calculus. Because remember, neural networks really are just a bunch of functions applied after one another. That's a key idea. So I'm going to go for a more kind of simplified example of like, we just have fully connected neural networks, right? So suppose one of your hidden layers takes some input X and it transforms it into some input Y. And we can think of the process as some sort of function f of X equals to, your activation, you apply the activation of Wx plus B equals to Y, right? Where A is the activation function, for example, sigmoid or ReLU or anything like that. And the important thing is f can be any function, right? Well, I'm just using kind of like a simplified example here, but f can be any function. And say your neural network layers are actually just like a sequence of functions applied in a certain order. So basically you put X into your first layer, let's call that layer F1, and you take the output of that layer, you put into F2, and you put into F3, F4, all the way to Fn, where each one of these Fs basically represents your layers. And again, F can be any function. It can be as simple as a fully connected layer, or it can be a convolution layer, right? Basically, it's just something that takes in some sort of hidden input X, or for the first layer, the actual input X, and then it does some stuff to it, usually something to do with matrix calculus or something that we can describe with matrix calculus, and it gives you an output. So we can kind of think of or model our neural network as a kind of composition of these functions. And at the very end, we add something called a loss/cost function as well. Let's just call it C. Again, one of the things with machine learning literature is this sort of notation is never consistent, right? People use all sorts of variables that varies depending on the textbook, depending on the paper. So one of the main things about reading machine learning papers is actually just the first step is just figuring out what the hell their symbols mean. So this is just happens to be the symbols that I came up with. It is not the best symbol. It is probably not the standard, but the idea is neural networks can be modeled as just a bunch of compositions of functions, right? And you can break these functions down as, as deeply as you want. For example, you can break them down into functions that individually does addition, multiplication, subtraction, concatenation, stuff like that. Or you can abstract them out and say, this is our first layer, this is our second layer, this is our third layer, et cetera, et cetera. And when we compose all these together, we get some outputs, we put it through a cost function and we get a loss function. So that's how we can sort of model neural networks from a high level. So then what we can say is, then the gradient is this, right? If we have the weights W, again, for every single layer, it usually will have different weights and biases, but I'm just kind of encompassing all of that into one big W, right? We can say the gradients is just, the partial derivative of our loss with respect to our weights, right? And this thing, right, this gradient will be the exact same shape/dimension as the weights that we're taking the partial derivative to. Because what we're basically doing is we're saying, because our kind of C here, our loss is just one scalar, what happens is the first entry of our gradient is basically the partial derivative of our loss with respect to the first entry of our weights. And the second one will be the second entry of our weight, third, fourth, et cetera, et cetera. And the question becomes, how do we calculate this? Does anyone have any idea of how we may be able to do this? Again, we have we have a bunch of function composition. We're applying functions right after one another, and we're trying to figure out the derivative of the outputs with respect to the input, but then we're trying to use these intermediate functions. How can we do that? Yes.
Lots of chain rule.
Lots of chain rule. That's exactly correct. So first, what I actually want to do is to reformulate the notation. So even though f1 of x and all the way to our cost function are all functions that take in some inputs and sometimes y, which represent your input being passed through the model, it also depends, this function itself also depends on your weights, right? Your weights for every single layer. So the functions really are, f of x, w1, f of x, wn, stuff like this. And a lot of times we can even ignore the x because the x is almost part of the function because x isn't what we're changing, right? We're not trying to modify x. The thing that we're trying to modify is our weights because that's what gradient descent is. We're trying to nudge our weights around so that we're minimizing the loss. So we only care about how the weights affect the model. We sometimes just omit the x and the y for that reason. So with that in mind, let's come up with the first attempt of trying to do backwards propagation, which is basically, let's compute the gradients with first principles. Some of you may remember this in high school calculus or math 31A, but this is the definition of a derivative, right? What we can do is we're going to say, okay, let's just take every single entry of our weights, nudge it by some really small value epsilon, right? And then so basically we keep all the other weight entries the same, but except for that one particular dimension, we nudge it by a little bit and we calculate how much change that has been. And we say, okay, that's the kind of gradient for that first entry. And we do that a bunch of times. The good thing is you can always use this method, right? This method doesn't have really any issues of like sometimes you may have functions that are not differentiable and you may have something weird like that. You can have any arbitrary function here. You don't even need PyTorch. You can do this with anything, even when you don't know what f is. So sometimes you're given a machine learning model, they don't have the access to the gradients. So but you will have access to the inputs and the outputs, and you may be able to do something like this. The bad thing, however, is that this is very, very inefficient. As let's say you have 100,000 weight dimensions, you will have to evaluate f 100,001 times because remember you have to evaluate f at the current point. Plus, it may be imprecise because we may have numerical errors. So with that in mind, this is not really what people do nowadays. In fact, one of the main reasons of things like neural networks have been developed for a very long time, right? Like even back in the 80s, people have came up with things like the neo perceptron, things that almost looks like CNNs nowadays. But the biggest problem back in the days is people didn't have a way of training those things because they're like with very small neural networks, like basically one layer perceptrons. We know how to basically solve to say this is the solution. We know the analytical solution to the lowest point. But with something like this, before we developed backpropagation, people didn't know how to compute gradients for it. People didn't know how to train this model. They knew that implicitly this probably worked, but they didn't know how to train this model. This is until in 1986 when I don't remember the authors, but when backpropagation was finally proposed. And as math student said, it is chain rule. So remember the chain rule? When we have two functions composed together, aka we apply f first and then we apply g, to be able to take the derivative of our output, or aka the function or the output with respect to x, we basically can first take the derivative of the output of f with respect to g, and then take the derivative of the output of x, of the output of f with respect to x, so like stuff like this, right? And the idea is we can use the same idea for neural networks as well. So since we have the network function, our C composed with all these things, what we can write is basically, well, first we can say, okay, this we can write as this, right? Because we are basically saying the partial derivative of our loss function with respect to the output of the last layer to our weights. Then we can say, okay, we can further expand this to say it's the partial derivative of the last layer with respect to the output of the second last layer and the second last layer to the weights. And we can keep going a bunch of times until we have this really long kind of multiplication or composition of this is basically chain rule, right? We're kind of using chain rule to slowly work our way from the back all the way to the front, from the outputs all the way to the inputs to say, this is our gradients. This is how we can analytically compute our gradients, right? Does it make sense what's happening here? Any like thumbs up if you are cool with this? Okay, so that seems pretty great, right? Like we can just do this, but the issue is, what do these partial derivatives really mean? Right? We have done partial derivatives of two constants before, right? We have done partial derivatives of in like math 32A or something like that, of a scalar with respect to a scalar. The value is a scalar. However, with a lot of these things, like our fn and fn minus 1, we are basically taking the partial derivative of a vector output with respect to a vector. What does that mean? We're taking the derivative of a vector with respect to a vector. We know the derivative of a scalar with respect to a vector is just the gradients. But what does it mean for us to have a derivative of a vector with respect to a vector? And I'm going to show you what that means with an example. Suppose we have the outputs of the second layer of some neural network being y, and a third layer of our neural network being z. Or like we put in y to here to get z. So where F2 maps a 2-dimensional x to a 4-dimensional y, and F3 maps a 4-dimensional y to a 3-dimensional z. So you can imagine kind of our x and then y becomes 4-dimensional and then z becomes 3-dimensional. Then what we can say is when we're calculating this expression here, or more precisely, the derivative of z with respect to y, it is this 3x4 matrix below, right? 3x4 matrix below, and I want you to notice that basically what it is, it has a dimension of outputs times input, right? Outputs times input. And we have this matrix, and this is called the Jacobian of F. Has anyone here heard of the Jacobian? Like, let's say in Math 32A. Yeah. So when you saw the Jacobian in Math 32, you probably thought, how am I going to use this? This is how you're going to use it, right? In machine learning, everything is the Jacobian. You basically just keep trying to compute the Jacobian or some sort of form of the Jacobian, and that's exactly what you're doing. So because the Jacobian is just a matrix, and this is how the Jacobian is by definition the derivative of a vector with respect to a vector. This is really just a series of matrix multiplications, right? And again, you can verify that the matrix multiplications are still satisfy the chain rule in higher dimensions, because remember the dimensions of all of these is output times input, right? We have output times input, output times input, output times input, and the output of this layer is the same as the input. Oh, sorry, the output of this layer is the same as the input. The input of this layer is the same as the output of this layer. So the dimensionality matches at the very end, right? So how does this work in practice, right? How does PyTorch know what the partial derivatives are? And the idea is this. Every PyTorch model has two types of operations. The first type of operations is something that PyTorch defines, and then the conv2d, which is convolution, our convolution layer, and the linear, our fully connected layer, our ReLU, batch norm 2D, so batch normalization, but with 2 dimensions, et cetera, et cetera. Because these operations are predetermined, PyTorch knows what the partial derivatives should be. Because if you just sit down and work through the math, because you've predefined these operations, you're able to calculate what the partial derivatives are. So for example, with f of x equals wx plus e equals y, we're able to say this is our partial derivative, right? We're able to define this and say this is how we're calculating this, right? Particularly Python. However, there's another type, which is Python operations. For example, if statements or addition, literally anything, right? And that with those operations, with operations that technically we have never explicitly defined a backpropagation, a sort of derivatives for, how would PyTorch be able to, backpropagate through that? And the idea is this: all code operations can be broken down into a sequence of addition, subtraction, multiplication, and division, and other basic operations, right? So like exponentiating, for example, will be a type of operation. Concatenating two things together will maybe an operation. And we know the derivatives for these operations, right? And because of this, we can break any operation down, any valid operation between two tensors at least, down into these things. We're able to calculate the gradients because we know what this is. And that's kind of the power of chain, was that we can always break things down even further. We can abstract things out by basically pre-computing a lot of these kind of backprop derivatives. But if we don't know what they are, we can always strip it down to its barest level, which is these very, these primitive, what we call operations. And we know that the derivatives of. So how does PyTorch actually do this then? What PyTorch does is it tracks all torch.tensor objects as we pass them through models, loss functions, and other operations. Specifically, we tell PyTorch to only track the weights W, as that is what we are taking partials to. And we can specify for this tracking to not happen to save memory, for example, during validation tests and test process where we're not computing gradients. And the way we actually do this to only track the weights W is when you're initializing a PyTorch model with like n module, where you're doing like, self dot fully connected one equals to n linear, right? What n.linear is actually doing is within that object, it initializes one of our matrices and it sets a very important property of any, and it sets a very important property for the tensor that it initializes, which is tensor dot require grad or require gradients equals true. And what that tells PyTorch is we're doing backwards propagation and we reach that tensor, store the gradients for that tensor because we are going to be modifying that tensor. In this case, we're going to be modifying those weights. And this goes for anything that any operation that we can manipulate. For example, a convolution, right? Remember kind of like our list of filters for a convolutional neural network or a convolutional layer. All of those tensors will be set to require grad equals true. So when we're doing backwards propagation, PyTorch knows that is something I should store the gradients for. And because PyTorch knows the sequence of operations that takes us from input X to input Y, to output Y, because when you said require grad equals true, it tracks that tensor in particular. We will be able to take the partials with the chain rule, right? Any questions so far? Okay. So the way PyTorch tracks tensors is with something called execution graphs. And again, this is a very abstract version of it, right? But PyTorch basically keeps a version of this in its backend that you don't see. They abstract all of this away and it's stored in pieces within these tensors. For example, if you have like this sort of fully connected layer with tracking a bunch of neurons, you're able to kind of have this sort of back propagation layer where we get from our activation of our previous layer to the output of the current layer by applying our weights and biases, and then the next one by applying weights and biases, and then the final one by applying our label. And this process is called automatic differentiation, which is relatively self-explanatory. It does this automatically for you, and this is differentiation, right? So automatic differentiation is the general term we give to any sort of program or basically any sort of machine thing that allows you to automatically calculate gradients. Particularly, we propagate backwards from the class C until we reach a leaf in the graph. In this case, our weights and biases. To kind of visualize that, we start from this loss, right? We know the gradients of how do we get from here to here, how do we get from here to here? Because again, these are all operations we have predefined. So we basically go from our loss, get the gradients, and kind of come here, and just kind of keep doing that sort of multiplication that we talked about with that chain rule. And as we kind of populate, this computation graph, we reach any of these leaves, aka usually there are weights that don't really rely on anything else. We reach these leaves, that's when we say, okay, then the resulting gradient that we have here is added to tensor.grad. And this is the important part about why we do optimizer.zeroGrad, right? Because another thing about PyTorch tensors that's very important is it has a property or a kind of class property called grad. Whenever you have a tensor and you do requires grad equals true, it will initialize its own gradient object as basically an identical tensor to itself, but just all zeroed out. And it represents its current gradients. What happens every time when you do backpropagation is you do that whole chain rule gradient accumulation, matrix multiplication, matrix multiplication, matrix multiplication. When it reaches one of your trainable parameters, what it does is it takes that gradient, and because via these operations the dimensions will match, it will basically add that resulting gradient to tensor.grad. So the effect of doing that is if you call, for example, loss that backward, or if you do backpropagation twice, you basically add to tensor.grad twice your gradient. So your gradient will just be twice as large, right? And if you think about not zero, and that's what optimizer.zero grad does, it zeroes out those gradients because you don't want the gradients kind of property in your tensor to keep accumulating through the iterations. Because what happens is it will just keep adding and adding and adding to this tensor.grad to this tensor.grad object or tensor basically, and your gradient just becomes really, really large and starts exploding away. So. Does that make sense so far? Yes.
Just out of curiosity, is there a particular reason why PyTorch adds the gradients
Instead of just replace it?
Yeah.
So the reason why we just add the gradient is mostly for syntactical convenience, because sometimes we may not just have one loss. We may have 2 or 3 or 4 more losses, and that's for more complex tasks. For example, if you're talking about generative adversarial networks, for example, where basically you have a discriminator and a generator. The generator generates images. The discriminator tries to guess, is this image real? Basically, is it from a data set, or is this image generated by a generator? And when you train both of these at the same time, what happens is the discriminator will get better and better and better at distinguishing between actual real world images versus the images that a generator is generating. But since the generator is trying to fool the discriminator, it gets better and better at generating images. You're able to generate things depending on ideas like faces or birds or churches or stuff like that, right? And by the way, all of those things I've said have their corresponding data sets that are actually just for faces, churches, and birds. There's a reason why I said those things. But basically, with things like that, you will have actually 2 loss sources because you're actually calculating the loss with like 2 different outputs. And instead of having to add those 2 losses together and then backwards propagate them, you can just do loss.backward for both of those losses. And what happens is PyTorch just adds them together, and that's sometimes your desired behavior. Basically, the philosophy is kind of like, rather than overriding things, we're going to give you the choice, the freedom to override those things when you actually want to do so. Okay. Does that make sense so far? Kind of what's happening? Okay. So I guess before we continue, I just want to show you kind of like a real world mathematical example of it. So here's like a simple-ish example of backpropagation of something we just look at, which is like a fully connected layer. We have Wx plus b. You can basically define what these gradients are. For example, if you want to take the gradient of the loss with respect to our weights, in this case, our weights is actually a matrix, right? What ends up happening is you have the derivative of your y with respect to your weights. And again, this gets a little bit complicated because if you think about it, our y is basically a 1-dimensional vector, but then our w, our weights, is a 2-dimensional matrix. So technically, the Jacobian for this is actually 3-dimensional, a 3-dimensional matrix. But people have done the math, and in fact, you will actually be able to derive this. Not here, but like, and UCI has class that allows you to do that, like ECC 147, where you show that this is actually equivalent to this. But if you notice, basically what we can do is just, as we're kind of propagating forwards, we can cache this intermediate value. And we cache this intermediate value because we know when we're calculating the gradients, we use it, right? And same with same with b here, because b, remember, it's just an addition. The gradients basically just pass straight through it. So the gradients of b is just the same as the gradients of y. And this gradients of y, maybe like, how do we calculate this? Well, we calculate this by the subsequent layers, right? Because we may pass y into subsequent layers and we kind of propagate all the way through the step. So this is kind of like a step within backwards propagation. And to kind of show you how relatively complex these things can get, this is kind of like a relatively complex example. Again, we're not going to go through this, but like this is just like showing you that, yes, even for really complex operations, we can predetermine all of these, right? With something like batch normalization. Batch normalization is actually a relatively complex operation because you are using your current batch values, within your modification of every single entry in there, and you're using it in multiple different places. And what you end up with batch propagation, if you want to work out all the math, is that the derivative of the loss with respect to the inputs of that layer is this entire expression here. And these are kind of like the steps they can take to get there. And basically, what I'm trying to emphasize is just, since we can exactly define the propagation gradients of any reasonable neural network operation, we can essentially have just a bunch of 4 propagation functions predefined and their corresponding backwards propagation functions predefined that we use that are predefined. Then training a neural network just becomes doing a bunch of vector and matrix math. Right? So that's the idea. Okay, so let's get back to the code. And with that knowledge in hand, in our mind, try to understand what's going on here. So for every single training iteration, what we do is we first zero out our gradients. Basically, if you remember back here, right? When we initialize our optimizer, we're giving it a list of our parameters. This is a built-in function in the PyTorch model kind of, definition, in the module definition. We do dot parameters. It gets you a list of tensors that's trainable, right? A list of tensors that has required a grad equals true. And basically, because we're passing this in, the optimizer knows the tensors that it is optimizing. Therefore, when we do optimizer.zeroGrad, what the optimizer does is it says, okay, let's look at this list of tensors that we used to initialize it, right? We loop through every single one of these tensors. We look at their .grad, their .grad property, and we zero it. That's what it's doing. Optimizer.zeroGrad. And then we take our inputs, right? We take our inputs, we pass it through our model, and we get our predictions. And again, everything here is being tracked by PyTorch with that computation graph. And then we, take our predictions and then we put it into loss with our labels, and we calculate our, cross entropy loss, whatever loss we're using. And then this is where we're doing the backpropagation. Because remember, current loss is just a scalar, right? And what's happening here is when we do current loss backward, it basically starts from here and it just starts propagating backwards and starts storing our gradients whenever we reach a sort of required grad equals true. When we reach our, it starts storing the gradients into our model.parameters. Then we have optimizer.step. And what optimizer.step is doing behind the scenes is it loops through all the parameters that have been passed in here. And it says, okay, we have the gradient of that parameter, which is just stored in the .grad property. Then let's use that gradient to do gradient descent or some more complicated version of gradient descent with moving averages and whatever. But it uses that gradient information to then optimize your model, to then nudge your weights around so that hopefully you're getting to some sort of good local minimum. Does it make sense what's happening here now after we have gone through all that? Any questions? Okay, cool. So as a quick summary, I know this is very long, but basically this is how the whole backwards propagation pipeline works from start to end. When we initialize the model parameters is a list of all the weights and biases that's in the model. And again, these weights and biases can be things such as, your fully connected layer WNX, can be your, CNN filters, can be your scale and bias in your batch normalization, anything, right? And then you initialize an optimizer where you pass in your parameters, and because those are the tensors being optimized with SGD or its variants. Then optimizer.zeroGrad zeroes out all the tensor.grad attributes, all the model parameters, because tensor.grad is initialized to a 0 tensor in the same dimension as each tensor in model parameters. And we pass our train data through the model and then the outputs of that through the cost function to get our loss, which this whole process is being tracked by PyTorch with an execution tree or a computational graph that we kind of just saw there. Then loss.backwards backprops through this execution tree with the process that we just defined before, aka a bunch of chain rule and a bunch of predetermined matrix multiplication. And by doing so, it stores all the gradients in tensors.grad. And at the very end, optimizer.step loops through all the tensors.grad and performs the actual optimization itself. Any questions with this? Are we good? Okay, cool. So yeah, here's some helpful resources to understanding backprop a little bit better. Blue and Brown, I always love his videos. And if you want a bit more advanced, Stanford CS231N is kind of a legendary course as an intro to machine learning. It is pretty great. And yeah, since we don't have questions, next time we're going to be talking about, we're going to be basically having a PyTorch guided project where we basically take all the code that we kind of showed you in snippets, put them into one big notebook, and show you how you can train your own image classification tool from scratch. Thanks for coming. Hope to see you next week.